Right, so now I'm going to just say a little bit about transforming a initial value problem into a particular normal form so that then we can establish a theorem, it's like for the existence and uniqueness of solutions for that initial value problem. Okay, so the first thing to do is just change your variables. Okay, so let's say that we have the following boundary value problem: x double prime is equal to f of t and x. Okay, and x of a is equal to alpha, and x of b is equal to beta. And we want to rewrite this on the interval from 0 to 1. Okay. All right. So we do a change of variables. So we say that t is equal to a plus b minus as. All right. Now, because of that, s is going to be in the interval from 0 to 1. So if you have a relationship between t and s, like the following, as s varies from 0 to 1, t will vary from a to b. Okay. All right. So now it's like, let's look at what this looks like. So if s is so y is a function of s, that means that it looks like x is a function of t. Okay. So I want to have that kind of relationship, and then that means that x is a plus b minus as. Okay. So y prime s is b minus a, x prime of a plus b minus as, and then y double prime of s is equal to b minus a squared, x double prime a plus b minus as. Okay, so that with that in mind, I can rewrite the original equation, okay, in the following way. So let's label that 2. Okay, so we have y double prime of s is equal to b minus a squared, f of a plus b minus as, and then y of s. Okay. All right, and then y0 is equal to alpha, and y1 is equal to beta. Okay. So the basic idea then is that we want to reformulate okay, well, let me see. I want to formulate general results for boundary value problems. When sort of considering sort of a interval from 0 to 1. Okay. So basically, again, there's no real loss of generality, right? In reformulating, it's like a boundary value problem. It's like of this form. It's like into this, with the caveat that here it's like I'm only assuming the right hand side depends on x. It doesn't depend on x prime. Okay. All right. So let's look at an example of this. Let me maybe try to do it here. Okay. So let's say we have x double prime is equal to sine tx plus x squared, and then x of 1 is 3, and x at 4 is 7. Okay. So I can write down the change of variables. T is equal to, it goes from 1 to 4. right? T is 1 plus 4 minus 1 times s, right? That's 1 plus 3s. Okay. Then we want that y of s is equal to x of 1 plus 3s. Okay. All right. So you can look what that is. Y double prime is equal to b minus a squared. So that's 4 minus 1 squared, which is 9. 9 sine of tx. So that's 1 plus 3s. And then that's y plus y squared. Okay. And then y at 0 is equal to 3, and y at 1 is equal to 7. Okay. So this initial value problem, this boundary value problem got rewritten. That's this boundary value problem. Okay. So that's where we're at right now. Okay. So and then the next thing we want to do is we would like to transform these boundary conditions so that they're homogeneous, which is to say that these things are 0. Okay, so let's see what happens there. Okay, so this is for homogeneous boundary conditions. All right, so let's look at an example of this. Okay, this is an extension of what we had done before. Maybe I shouldn't have erased that. Okay, so let me just try to rewrite what we had before, right? So we had y double prime of s equals to 9 sine 1 plus 3s y plus y squared, and then y at 0 is equal to 3, and y at 1 is equal to 7. So we're going to add additional transformation. So we had started from x, now we have y, and we're going to transform it to z. So let's say z of s is equal to y of s plus, what I'm going to do is I'm going to find a linear interpolant between the data, 3 and 7. Okay, so this is going to be 4s plus 3, so minus. Okay, so when s is equal to 0, I get 3. When s is equal to 1, I get 7, right? So this term, it's like satisfies this data. Okay, so if I take this minus this, right, then whatever is left over, the z of s is going to have 0 boundary data. Okay, so with that, I have z of 0 is equal to 0, and z of 1 is equal to 0. Okay. All right, so I can differentiate z as before, right? So z prime of s is y prime of s minus 4, and then z double prime of s is equal to y double prime of s. Okay, so the basic idea then is that I can convert this to a new variable, right? I can convert this into a different equation, right? So let's call that 3, if you will. So z double prime of s is equal to 9 sine 1 plus 3s, which is t, right? So this is t. And then, okay, I have z of s plus 4s plus 3, right? So this is supposed to be y of s, right? Y of s is written as z of s plus this term here, which is what I've done here. Okay. Okay, all right. Then there's a y squared term. as a y squared term. So the y squared is z of s plus 4s plus 3 squared. And then you have z of 0 is equal to 0, and z of 1 is equal to 0. Okay, so the point then is that you can solve for z of s. Then I can invert all the transformations I had, right? Then y of s is equal to z of s plus 4s plus 3. And then x of t, right, is y t minus 1 over 3. Okay, so that's basically how you get from something that's like which involves this sort of standard form, and then where the interval is from 0 to 1, it's like, and the boundary conditions are 0, and then sort of transform it back to an arbitrary boundary data and arbitrary interval from A to B. Okay. All right. So that hopefully will give you some idea. Then again, now that we can show that, now we've shown that if you have a boundary value problem, it's like where the right-hand side just depends on t and x. Right, you can convert it into this kind of standard form. Let's state a theorem about the existence and uniqueness for that kind of problem. Okay. So the theorem is as follows. Okay, so this is for existence and uniqueness. Solutions of boundary value problems. Okay, so the theorem is that if you let f, which is the right-hand side of the differential equation, be a continuous function of, let's say, t and x, right, where t is in the interval between 0 and 1, close interval, and x is between, well, it's just finite, okay, then assume that on this domain you have a Lipschitz condition in the second variable. So f of t x1 minus f of t x2 is less than equal to some constant k of x1 minus x2, where k is less than 8, right? Then the 2-point boundary value problem y double prime is f of t and y0 equals to y1 equals to 0, has a unique solution. In sort of space of continuous functions from 0 to 1. Okay? All right, so that's the theorem. So let's try to see an example of applying it in practice. So as an example, x double prime is equal to 2e to the t cosine x, x0 equals to x1 equals to 0. Okay, so if I look at the difference of the right-hand side as I change x, right, f of t x1 minus f of t x2 is equal to df ds t some unknown point x3 times x1 minus x2. Right, this is just the mean value term. Okay, so x3 is between x1 and x2, and we know these are strictly between 0 and 1. Okay, so let's calculate that. So df ds equals to 2e to the t cosine x times minus t sine x. Okay, so we're just going to do a very crude estimate, right? So t times cosine x is going to be less than or equal to 1, and then the same thing for t sine x, an absolute value is going to be less than or equal to 1. So this is going to be bounded from above by 2e. Okay, and you can compute that. That's less than 5.437, which is less than 8. So, and you can check that f is a continuous function. F is a continuous function of t and x. Okay, so by this theorem, right, this two-point boundary value problem has a unique solution. Okay, all right. So this is just some existence theorems, it's like which apply when you're in this special case where you know, it's like the right hand side only depends on y and t, it doesn't depend on y prime. Okay, and it does have this homogeneous boundary condition over this fixed interval 0 to 1, but as we saw before, you can transform. It's like a boundary problem, a boundary value problem of this form with arbitrary boundary conditions and arbitrary interval from a to b into this standard form. So there's no real loss of generality in just looking at this, modulo the fact that the right hand side does not depend on y prime, right? Okay, so anyway, so let me just stop here for now.